So I just uploaded the flow graphs we're going to use today to the spectral analysis folder on the RU 2023 repository. So same thing as yesterday. And today what we're going to do is a bit technical, but it's also important. What we're going to do is twofold. We're going to see how we can use GNU Radio to do spectral analysis, and that means basically compute FFTs from our signals to see them in the frequency domain, and so to be able, through integration, perhaps for many seconds, to detect signals which are weak, either narrowband signals, which could be potential technosignature candidates, or wideband signals, which are quite common in radio astronomy, because in radio astronomy, when you have an emission process such as a spectral line, it's often wideband because of Doppler shifts or because of the intrinsic line width of whatever is producing the RF energy. The other thing we're going to do is to show how we can use GNU Radio to generate some signals with these qualities, either narrowband signals or wideband signals, so that we can generate signals with exactly the amount of power we want. Because if we want to test some detection algorithms, it's important to be able to generate signals with an exact signal to noise ratio so that we can check whether our algorithms work with that particular signal to noise ratio or whether they don't. And we will be generating narrowband and wideband signals. So I have my GNU Radio here. As the last time, I'm going to start from scratch. I have the completely built flow graphs also as a reference. I will be copying and pasting some formulas from that just to avoid making mistakes. I often make mistakes with these signal to noise ratio formulas, and I think that happens to everyone. But the key thing is to remind how to check that you are computing signal to noise ratio properly, and if you are not, how to fix your formulas. That's the key to doing things properly. So, okay, the first thing I want to do is to pull here a frequency sink. And as we have seen previously, the frequency sink can be used to display the frequency spectrum of a signal, but it's somewhat limited. And we will see some of its limitations today and how to improve that doing our own frequency sink. So something else I want to do is to put here a variable, because we are going to be playing with the FFT size in several blocks. So I want to define a variable, which is the FFT size, and I'm going to make it 2 to the power 16. You might know that FFTs can be computed efficiently when the size is a power of 2. So powers of 2 are very typical as FFT sizes. What else? This is a simulation, but still I need to simulate some particular sample rate. So the sample rate I'm going to simulate is 1 million samples per second, which corresponds to a bandwidth of 1 megahertz. And that is low compared with typical current radio astronomy or SETI telescopes, but it's good to do a simulation on the computer without spending too much CPU resources. What else? So every radio receiver has its own noise floor. We saw that with the RTL-SDR stick. The noise floor is both caused by noise on the receiving antenna and also by noise introduced by the receiver itself on the electronics. The way to simulate noise in GNU Radio is to use a noise source. So I'm going to pull here the noise source. And when we edit the properties of the noise source, we have the noise type. And this is usually set as Gaussian. Or the most simple type of noise that you will encounter in radio frequency signal processing is Gaussian noise. There are other different types of noise you can simulate with this block, but 99% of the time you will be using to simulate Gaussian noise. The other thing we can set is the amplitude. So a larger amplitude will make the noise signal larger or devote more power to the noise signal. I'm going to normalize the noise amplitude to 1 because this is a simulation. Amplitudes do not play any physical role. They are not directly related to physical quantities. They are just abstract measurements. And what I'm going to do is to normalize everything so that my noise power is 1. And then the noise of the signals of interest I'm going to simulate will be determined in terms of this noise power, which is 1, and the signal to noise ratio that I want those signals to have. And finally, we have the seed parameter. As you can imagine, the noise is generated in the random way, and so the computer doesn't really generate random numbers. It generates pseudo-random numbers, and it does so in terms of a seed. So if you want to get always the same results, you use always the same seed. And if we were to have several noise sources, and we will do so, the way to ensure that they are generating different noise signals is to use different seeds. So, okay, so far nothing too difficult. Also, I'm going to put here a throttle block. And the throttle block, as I mentioned on the previous session, is used to limit the amount of data that is flowing through the flow graph to real time or to any other arbitrary rate to prevent 100% CPU usage. And something I didn't remember to do is to set the FFT size. So here I have a drop-down list, but this is also a text box. So I can do NFFT. And what's going on? Okay. Yeah, what's the FFT for reference? Okay, I do have not 2 to the power 16, but 2 to the power 14. Because as we saw, there is already one limitation of the FFT sync here, which is apparent. The maximum FFT size you can do is 32,000 points. And that is quite limiting. Often for detecting narrowband signals, especially in a wideband bandwidth, we would like to use much larger FFT sizes. And with this block, we cannot do. So anyhow, we're going for 16,000 points. And I'm going to save this as spectral analysis simulation 2. And if I start the flow graph, what I can see is just there is uniform noise here at about -50 dB level. The level has to do with the FFT scale normalization, so it's not something we should worry about. What we should worry about is relative measurements between the noise and our signals, as we will see. And yes, the noise is a random process, so we can see the spectrum is jumping up and down slightly. We can do some FFT averaging. For example, we can set high FFT averaging, and we can see that the noise floor tends to average out over time. And already we can see something about how this averaging is done, because this is another of the weaknesses of the frequency sink that we are using to display this signal. There are basically 2 types of averaging that are the most simple averages. One of them is called one-pole IIR filter, and that's essentially taking the previous signal multiplied by a large number, for example, 0.99, and add the new signal multiplied by a small number, for example, 0.1, and the 2 numbers should add to 1. So what we are doing basically is to have an average which tends as an exponential decay process to the new value. So if I were to change the noise power, the signal would change, for example, to this level, but it will change slowly following an exponential decay or exponential growth. Because of how this averaging is done. The advantage of that kind of average is it's very simple to compute. Also, you have one output per input, and that's convenient because we can see that the plot here is updating quite fast, but it's not the most sensitive. The most sensitive way to do averages is with something which is called an integrate and dump, which has to do with a moving average. Maybe you are familiar with a moving average. And an integrate and dump process is as simple as taking a block of samples, for example, 1,000 samples, summing those up together, or rather computing an average of 1,000 samples, and then that's our result. So the advantage is this is better than the other kind of average. The main disadvantage is since we are grouping 1,000 samples and then producing only one output sample, we are reducing the data rate, so things will not update as fast. For example, if I want to do 1 second averages, which means group all the data for 1 second, then compute its average, I will only be able to display one curve per second, and my plot will keep jumping every second, or will keep updating every second. So instead of here where we can see that this is moving constantly, it's updating tens of times per second. If I do 1 second averages with this method, then the plot will only be able to update once per second. Okay, so so far this is not so interesting. This is just the noise floor of our simulated receiver. What we are going to do next is to simulate a narrowband signal. And we already know how to do that. We did that for audio signals, and that is done with the signal source. We know that the cosine signal simulates a narrowband signal whose spectrum is just a CW carrier or a Dirac delta, if you wish. And what I'm going to do is to set entries for the frequency, and I'm going to do here narrowband frequency in kilohertz. I'm going to set this, for example, to 10 kilohertz by default, but this is an entry field, so we can change it when the flow graph is running. And the frequency is supposed to be given in hertz, but I have wanted to do my entry in kilohertz, so I need to transform narrowband frequency. And then I also want to control the amplitude, but for 1 second, let's set this to amplitude 1 and see what happens. The other thing I need to do is I want to add the noise signal and the narrowband signal together. And to do that, I can use add block. So there we go. Now we can see our narrowband signal, and it's here at 10 kilohertz as expected. So 0.01 megahertz is 10 kilohertz. And something we can note is the relative signal level, or the relative signal to noise ratio. So this is about -9 dBs, and the noise floor is at about -50 dBs. And we might say that the signal to noise ratio of the signal is 41 dBs, if I'm not mistaken, because 50, or rather -50 minus -9 is 41. So the difference here is 41 decibels. But we need to be sure what we mean by the signal to noise ratio of this signal is 41 decibels. Especially, we need to be able to convey some measurement which does not depend on the way we are processing things. And one of the processing parameters we are using is the FFT size. So let me demonstrate how things can change if I change the FFT size. I'm going to make it twice smaller. So rather than 2 to the power 14, I'm going to do 2 to the power 13. And then I get the same thing. There are now only 8,000 points here, but it's difficult to realize unless we count. But what we can see now is the noise floor is no longer at 50 dBs, it's more or less at 47 dBs, yet the signal is at -9 dBs. So the signal to noise ratio would appear to have dropped by 3 dBs, because the noise power appears to have increased by 3 dBs. So what is going on here? Because apparently, just reading from the FFT, we are not able to give coherent or a consistent measurement for the signal to noise ratio of this narrowband signal. So what's happening is really something quite simple. The FFT measures power in each of the FFT bins. So what happens is here we have 1 megahertz of bandwidth, and we are dividing that 1 megahertz of bandwidth into 8,192 bins or buckets of frequency. I'm going to calculate how much hertz per bucket. So that's a division. On another screen, I'm dividing 1 million over 8,192, and that gives me 122. So that means each of these FFT bins, and in fact, we can show them by doing here a line marker circle. So each of these points represents the power within 122 hertz. So when we're measuring noise, we are measuring 122 hertz worth of noise. And then when we are measuring here the signal is narrowband, so it is completely contained inside one of the FFT bins, and this point corresponds to basically all of the power of the signal. We also have these points because of something called spectral leakage, FFT window, etc. And those are more technical reasons about the FFT. So what happens is typically we use a window with the FFT, and the window we choose shapes the kind of peak that we see here when we have a narrowband signal. And rather than be completely concentrated in one FFT bin, the signal power will be spread over a few neighboring bins and will decay like so. And I can go back here and show you how to change the window type. So there are several different windows you can choose. And for example, rectangular is in one sense the worst one, because I'm not sure if I'll be able to show this properly. Yeah, maybe it's easy to see. So what happens with a rectangular window is that I want the markers here, is that this spectral leakage tends to be wider. So the amount of bins affected by our narrowband signal tends to be wider with the rectangular window. So that's the reason why other kinds of windows exist, and there is some amount of design depending on what aspects of the FFT you want to enhance. It is not possible to have something that works the best in all performance parameters that people are interested in. Okay, so now let's try to come up with a quantity that serves to define the signal to noise ratio of the signal source. And this depends on the field or area in which you're working. But in communications, where I come from, it's quite typical to give the signal to noise ratio reference to the noise power in 1 hertz. So we saw before that the noise that the FFT is measuring corresponds to the noise power in 122 hertz. And if we go back to the original FFT size, then we would have here the noise power in 61 hertz, because 61 is half of 122. And that's the reason why when I measure here, I measure minus 50 dBs, and with the other FFT size, the noise was at minus 47, just because we are taking half amount of noise bandwidth in each FFT bin now. So measuring signal to noise ratio in 1 hertz of bandwidth is a good way to normalize things. And what we can do, I'm not sure if everyone is so familiar with dBs. I started speaking about dBs because the plot here has dBs on the units, but maybe I need to do a very short recap of dBs. So the idea about dBs, yeah, there we go, is that 10 dBs represents a change in power of 10, and it's multiplicative. So 20 dBs is 100, because essentially if you want to translate from dBs to linear unit, you divide your dBs by 10. So 20, for example, divided by 10 is 2, and then you raise 10 to the power 2 in this case. So 20 dBs represents a change of 100. 30 dBs would be 30 divided by 10 is 3. 10 to the power 3 is 1,000. So this is a change in 1,000. This is a change in 10,000. And so dB units are a very good way to plot quantities which have very different powers in this case, as it happens with any kind of logarithmic scale. So here before we were speaking about 41 dBs difference in power. That's slightly more than 10,000 times. It means that the power of the signal here is 10,000 times more power than the noise in 122 hertz or in 63 hertz, as in this case. If I want to compute how much power the signal has compared to the noise in 1 hertz, what I have to do is to multiply that 10,000 times by 61 hertz, because if the signal is 10,000 times more powerful than 61 hertz of noise, it will be 61 10,000, so 610,000 times more powerful than 1 hertz of noise. And when working with dBs, what we can do is to add the add 10 times the logarithm base 10 of 61. So let me compute that. Maybe I can also share this here, so to show the calculations. So the calculations I was doing was just the bandwidth divided by the FFT size in both cases. And now I'm doing 10 times the logarithm base 10 of 61, which is what I got here. And I get 17.8. So this means that, okay, if I want to give the signal to noise ratio of the narrowband signal referred to 1 hertz of bandwidth, then that would be 41, which is what we measured before, plus 17.8, and this is 58.8. And it's more or less okay, because we expected to get 60. I will explain why we expected to get 60 in a moment. And of course, this 17.8 will change depending on the FFT size. So for example, if we do with 122, what is going on? Yeah, indentation. Then rather than 17.8, we get 20.8. So the difference in 3 dBs we saw on the FFT plot is now compensated when we add this correction factor, which depends on the FFT size. Okay, so let me see. Yes, what I want to do is to add here an entry field, and this is going to be the narrowband power. And the technical term for power related to the noise power in 1 hertz is CN0, because C means the carrier power, and carrier is just another name for signal. And N0 by convention means the noise in 1 hertz of bandwidth. Every time you see N0 in some formula, is the noise in 1 hertz of bandwidth. And dB.hertz, it's just a way to remind us that the noise is being measured in 1 hertz of bandwidth. So I'm going to set this at 60 for the sake of the example. And now here is where I'm going to cheat a little bit, and to avoid mistakes, I'm going to copy the formula from the flow graph I have already done. But let me explain why we have this formula. So the first thing to take in mind is that here we are setting the amplitude of the signal, not the power. But there is a relation between amplitude and power. Power is amplitude squared, amplitude to the power 2. So if we have power and we want to get the amplitude, we need to take the square root. So that's the reason we have a square root here. Then the expression inside is computing power. And the way we compute power in this case is as follows. We have the narrowband power. I have called this narrowband power. So we have narrowband power, but this is in dB units. So the way to convert between dB units and linear units is, as I was saying before, to divide by 10 and then raise 10 to that power. So this is the noise power, the signal power in linear units. This will be 1 million because 60 divided by 10 is 6 and 10 to the power 6 is 1 million. But then what happens? What happens is that the amplitude 1, which also corresponds to power 1 because 1 squared or the square root of 1 is 1. That is the main reason why I decided here to normalize the amplitude to 1. So the power 1 corresponds to the noise power across all the sampling rate, across all 1 megahertz. So if we want to calculate how much noise power is in 1 hertz of bandwidth, we need to divide 1 by the sample rate. So we need to divide 1 by 1 million. And so the noise power will be 1 divided by 1 million, or 10 to the power 6. 10 to the power minus 6, sorry. And here what we are simply saying is that the signal is the narrowband power appropriately converted to linear units multiplied by that 1 divided by sample rate, or 10 to the minus 6, which is the noise power in 1 hertz. So hopefully that is more or less clear now. As I said, it's quite easy to get confused with these formulas. For instance, sometimes there is a factor 2 somewhere because of real sampling. Complex sampling makes things slightly more easy for this kind of formulas. But hopefully now you have already one example showing this, and you will also have the tools to check if this is working more or less correctly or not. So, okay, we have the amplitude, and something is wrong about this formula. MP is not defined, so I'm using MP for NumPy because I'm used to working in NumPy, but I need to import NumPy in this GNU Radio flow graph as I would do in any other Python script. And now we see that the amplitude we get back is 1, which is the amplitude we had before. So that's the reason why I said we were expecting to measure a signal to noise ratio of 60 dB hertz with the FFT plot when I was saying we have obtained. Yeah, sorry.
Can you show me again how you import NumPy in the graph?
Yeah, there is this import block. So drag and drop import block. And then what you need to do is to type here an import statement. So import NumPy as MP.
Okay, thank you.
And if that worked correctly, I guess you get some indication, at least it is not red. So for example, if I do NumPy F, which doesn't exist, then it goes red. So that's the way. And if you want to import multiple Python packages, you can do so just by putting several import blocks.
Okay, thank you.
Thanks for the question. If anyone has questions at any moment, just ask. And also feel free to ask in chat. I tend to have the window chat open also. So as I was saying, amplitude of 1 corresponds to a CN0 of 60 because of how the math works out. In this case, basically it boils down to this 1 million, which in base 10 is 10 to the power 6. And then what we got with the FFT was 58.8. So there is an error of 1.2 dBs. And maybe let's try to discuss a little bit why we get an error of 1.2 dBs. And the first reason why we get an error is pretty clear. So the noise is so jumpy, I would need to average out both over time and over frequency. If I want to take a very precise reading of noise, we can exploit the fact that the noise floor is flat. This happens in this simulation because it's a wonderful simulation. If you have a real world receiver, the receiver passband will have some shape. It will not be perfectly flat. And it's common to do an estimation of the receiver passband or a calibration of the receiver passband with the goal of making the passband as flat as possible by applying the calibration, because that makes things easier. And when we have a flat passband, if we want to measure the noise power, we can average not only in time, but also in frequency. I could grab all these points and all these points not affected by the signal and perform an average. But working here graphically, you can see that I might have an error of maybe half a dB while trying to guess the real noise value. So that's one reason. And the second reason I already mentioned slightly, which is if we want to do here the points to see it better. So there is something which is called scalloping loss. And that means that some fraction of the power of our narrowband signal gets spread to neighboring FFT bins. So the signal power, rather than being just this value, is this value plus these two, plus these two, plus these two, and perhaps a small contribution here, which we can already ignore. And if we add, we need to remember that powers do not add as dB quantities. We need to do the conversion to linear powers. So we would convert this value minus 8 point something. We would convert this value, convert and add all of those, and then convert back to dBs if we want. I'm not going to do that, but if you need to do so, it's easy to do, especially if you're programming in Python or any other language. And also something important is that the spectral leakage you get, the scalloping loss, depends on the FFT window. And there is something called flat top window, which essentially gives you a flat top, and that's intended to reduce scalloping loss. So now that I'm showing how this works, it appears to make the problem worse. But the important thing is that if I change my signal frequency, so I'm going to turn down the averaging to make this easier to see. So for example, if I change it, I want actually to have something which is small. Half an FFT bin would be ideal. So, but that's probably like so. So if I change like so, you can see that the signal moves. Now it's more present on this bin. Now it's more present on this bin, but the measurement hasn't changed much. If I have now the rectangular window, which is the one with worst scalloping loss, we can see that the signal is here, but when I do this, or maybe let me try with 3. Yeah, with 3 is pretty apparent. So if I put 3 here, or maybe even 4, yeah, this is pretty bad. So what happens with the 4 here is that now the signal is completely between these two FFT bins. So the signal power has spread between the two, and basically the peak we see has dropped by 3 dBs because the power is spread. And we can see how this changes. So, oops, sorry. You need to remember not to type something which is not a number in one of those entry boxes, because if not, the flow graph just terminates. So anyhow, rectangular window we had, and we also had these points. So we can see here, for example, it's at minus 0.28, and when I go 0.4, it decreases basically by 3 dB because now it's spread over 2 bins. Whereas if I do the flat top window, then as the name indicates, this is flat. And if I go 0.4, it moves, but since it's flat, it doesn't decrease. So that's one of the advantages of the flat top window. But then you need to figure out how exactly to measure your signal power, because you cannot really add all of the FFT bins here. You need to do some math. So maybe this also gives you an indication of why there are so many different FFT windows, and the GNU Radio doesn't even offer you by default all the very different FFT windows that you can find on the literature. And if you are doing some work which needs to go to a very fine detail with FFTs, maybe choosing the FFT window to focus on exactly what you need is a good idea. So, okay. This shows how to generate narrowband signals and how to measure their power, even though the FFT is not perfect to do that, and also how to set their power here. Another kind of signal that we are interested in is a wideband signal. And the wideband signal basically looks like noise, but it's oftentimes limited to a certain bandwidth, either because it's a communication signal and the communication signal can only occupy a certain bandwidth because that's the bandwidth allocated to that communication service, or because it's a natural radio astronomy spectral line, which has a particular line width because of Doppler effect and physical reasons. The way to generate this in GNU Radio, or a way to generate this in GNU Radio, because there are many different ways, is to start with a noise source. But if we don't do anything, this will be the same as here. I'm going to change the seed before I forget to get a different noise. So we need to do something to limit the bandwidth of the noise. And we can do two things. The first is to pass the noise through a low pass filter or through any type of band pass filter. By doing so, we are removing the noise we don't want, and we only let through the noise in the pass band of the low pass or band pass filter. But there's another interesting way to generate our noise, which is to use a polyphase arbitrary resampler. And the motivation to do this is as follows. Let me come back to the previous plot. So the noise source we have here is generating 1 megahertz of noise because the sample rate is set to 1 megahertz. If we were to somehow include this 1 megahertz of bandwidth into a larger bandwidth, for example, 10 megahertz, this noise source would only occupy, if the conversion is done properly, it will only occupy 1 megahertz of bandwidth, because originally it was only intended to be 1 megahertz of bandwidth. So what we can do is to generate noise at a lower rate and then use this resampler block to include that noise at a lower rate into our 1 megahertz bandwidth in such a way that the noise only occupies the original bandwidth that it was simulated at. So let me show what I mean by that. And I'm going to add an entry for the, here I'm going to do wideband width. Also in kilohertz. And maybe let's try to go with 10 kilohertz, for example. So if I want to include 10 kilohertz in 1 megahertz, the resampling rate or ratio I need to do is the sampling rate divided by the wideband width. And as before, I multiply by 1000 because this is in kilohertz and I want everything to be in hertz. And this is not surprisingly 100. So what we do is generate noise samples. And for each of those noise samples, we are resampling. We are generating 100 samples. So for each input sample here, we have 100 samples at the output. The sample rate here is 10 kilohertz, and the noise fills completely the 10 kilohertz bandwidth. And the sample rate here is 1 megahertz, and the noise, as before, only fills 10 kilohertz bandwidth. What 10 kilohertz? The central 10 kilohertz bandwidth. We might move the noise in frequency if we want, as we will do later on. Yeah, for some reason, this has disappeared. So this was 183 multiplied by wideband width, I think. And the rest of the parameters we can leave at default. They are used if you want to customize the resampling filter, but oftentimes the default one is the good one. So let me change the number of inputs in the add block to 3. And now we can see how our noise looks like. So if I set medium average, then I can measure this and it goes from -5 kilohertz to +5 kilohertz. So here is my wideband signal, which is just 10 kilohertz of noise. Currently, it is at the middle of the spectrum. And I can change here, for example, if I want, oh, sorry, this is the narrowband signal, but let me take it out of the way. If I put here 100, then we get 100 kilohertz of noise, and we can see something already, which is that the noise power seems to be dropping because the noise is spread over more bandwidth. Here, the amplitude is set to 1, and as before, that corresponds to the amplitude in the bandwidth in which this noise is generated, which now is 100 kilohertz. So the noise spectral density, which is the technical term, that means how much noise per hertz, is that 1 divided by 100 kilohertz. And if I set this to 10 kilohertz instead, I have the same noise power, but it's more concentrated. So the noise spectral density is larger. Okay, so this is a good way to generate noise. And something I want to point out is that in a GNU Radio flow graph, there is no explicit indication of what is the sample rate in each of the connections. It is up to us who are designing the flow graph to know and keep track of what is the sample rate. That is very easy to do when there is just a single sample that applies throughout the whole flow graph, and we have the sample rate variable to help us. But oftentimes in a flow graph, there are sample rate changes, such as this resampler. And then we need to know that this is 1 million samples per second here, but it's only 10,000 samples per second here because of the 100 resampling. Okay, if I want to move this noise signal in frequency to place it in a different location other than the center, there are multiple ways to do that. And one of those ways is to multiply the signal with a complex exponential. Because you might remember that if you multiply a signal with a complex exponential, then that is equivalent to a frequency translation on the frequency domain. The reason is because of Euler's formulas. When you multiply two exponentials, the exponents add, and the thing you put on the exponent of a complex exponential is the frequency. So when you multiply two complex exponentials, their frequencies add, and it also happens for an arbitrary signal. If you have an arbitrary signal, such as this noise here, and the complex exponential, which is generated by this signal source, even though it says cosine, since it's blue, which means complex data type, it's a complex exponential, then this is a frequency shift. And we can do the same. We can do here wideband frec to set the frequency we want this at. And what we need to set is the amplitude to 1. So the amplitude always needs to be 1 at this point, because we do not want to scale our noise signal. And then wideband frec. And with this, quite easily, I have already something that lets me move the noise. Yeah, by default, this was set to 10 kilohertz, so maybe minus 200. And now it goes to minus 200 kilohertz. And this already shows how you can simulate a fairly complicated spectrum by adding different narrowband and wideband signals, placing them wherever you need. The next thing we want to do is to show how to adjust the amplitude of the noise signal, or to adjust the power in the same sense we did with the noise, with the narrowband signal here. But for the noise, oftentimes it is more common to use a different way of measuring power, which is just comparing spectral densities. Because since noise is spread over a large bandwidth, maybe it's not so convenient to measure all the noise power in this 100 kilohertz bandwidth. Maybe it's more convenient to measure the noise power in any bandwidth, for example, 1 hertz bandwidth, and compare it with the noise floor power in the same bandwidth. And since this is flat and this is flat, the bandwidth we use to measure doesn't matter as long as it's smaller than the bandwidth of this whole signal. Because if we measure here things in 1 hertz and here things in 1 hertz, we will get some value. If we measure things here in 1 kilohertz, we get 1,000 times more. But if we use the same bandwidth, so 1,000 kilohertz here, we also get 1,000 times more. And since we are only interested in quotients, so dB difference is the same as dividing, the 1,000 factor, which is common on both, disappears. So that means we do not care about the bandwidth, or it doesn't matter what bandwidth we choose to use. And we want to come up with something which is signal to noise ratio. And in this case, it would be something simple, such as minus 50, minus 30, it would be 20 dBs. And we will see these 20 dBs has to do with these 10,000, or rather with the 100 here. It's no coincidence that we have 100 here and 100 is 20 dBs. Okay, so how to compute this noise power or wideband power? Wideband, I should say SNR rather than power, because power is usually referred to as in an absolute scale, and SNR refers to signal to noise ratio, which is what we're doing. We're comparing the signal power with the noise power. So wideband SNR, and this is in dBs. Let me set 20 to see that we get the same values here, amplitude 1. And then what's the formula? You might even guess already. So this is basically, yeah, I want to get the correct formula. Where do I have this? Okay. Yeah. So the amplitude for this is the square root, because we need the amplitude. And we want to use the wideband power divided by 10. So this gives us the noise signal to noise ratio in linear units. But we need to adjust for the scale, because as I was saying, amplitude 1 is for the noise in 1 megahertz. So for the noise in 1 Hertz, it would be amplitude 1 divided by 1 million. But then I want the noise in wideband width. I think I called it. And I think that's equivalent to the formula I have on my sheet, completed flow graph. Yeah, it is. So I need to multiply by 1000 because this is in kilohertz. And then you can see I get amplitude 1. This is just, again, a conversion to linear units. And now this is basically how much signal bandwidth we have in comparison to how much total bandwidth we have because of how noise power scales with bandwidth. And we can see that if we set things to high average, get this out of the way, let me see. So frequency 50 kilohertz, for example. Now the noise is here. We can measure, and the difference is minus 30 or thereabouts, or rather minus 50, minus 30. So the difference is 20 dBs, as we have here. If I set 30 dBs, what's happened? This is completely unexpected. So let me repeat this. I'm changing the wideband SNR, and what happens is the complete noise floor is going up. Yeah, I see what the problem is. The problem is I have set the formula on the wrong noise source. So this should be 1, and this should be the formula. So once again, high. This should go to a frequency of 50. And we have 20 dBs of signal to noise ratio. If we increase this to 30, then this increases. It increases slowly because of the average we are using. And now we have minus 20 in comparison with minus 50. So this is 30 dBs above the noise. Now, what do we want to do? What we want to do is to really detect weak signals. And by weak signals, I mean something that maybe has a 0 dB signal to noise ratio, or even less than that. We will see what happens with 0 dB signal to noise ratio and discuss why that happens. And maybe a narrowband signal of 20 dB hertz or something, or even lower. We want to detect signals as weak as possible. And already for the narrowband signal, we can see that, yeah, it's still there because we know that it's still there, but it's fairly difficult to see if we didn't know. And it even goes down sometimes. So sometimes it's even weaker than the surrounding noise. So definitely we need some kind of improved processing. And also with the noise, what is happening here? So if we measure minus 50, minus 47, the reason is 0 dBs means the noise power density is the same as the signal power density. So when the two of them combine, the total power increases by 2 because we have two things which are the same power, they are adding together. So the total power increases by 2, and we see an increase of 3 dBs. 3 dBs is the same as an increase in power by 2. What this means is that if we are able to see as a 3 dB increase a noise power or a noise signal to noise ratio of 0 dBs, we might even try to go negative and ask ourselves what happens with -1 or even -2 or even -8 or something. And now that the average is disappearing, we see that -8 is not possible to detect with these processing settings because this is slightly larger than the rest of the noise floor, but the noise is random and the variation here is large enough that the small increase caused by the signal is impossible to detect. There is something called the radiometer equation, which tells you, depending on the detection bandwidth you use, depending on how much averaging you use, how much signal to noise ratio you can detect with something called a radiometer, which basically compares two powers, which is what we're doing here, comparing the power of signal plus noise together in this region, sorry, with noise only in the rest of the noise floor. Okay, so how to do an improved signal processing? The trick is to do in a certain way our own frequency sync, and we will do so by using FFTs. To do an FFT, there is the FFT block. As you know, the FFT transforms from time domain to frequency domain or vice versa. And it needs an FFT size, which we had set as NFFT. And then there is a window. So the window, you can choose whatever window you want. There are window functions you can call, and these evaluate your window. And if I'm lucky, yeah, I can show you the window is just a vector of NFFT numbers, and you could even move this over to some Python script and plot the window or do whatever you wanted with it. And oftentimes you want a rectangular window or no window, so you can do that with this empty list, square bracket. In Python, these are two square brackets, maybe like so is easier to see. Then forward and reverse means whether to convert from time domain to frequency domain, that's forward, or to go backwards from frequency domain to time domain, that's reverse. Shift is the same as FFT shift. If you've used any FFT package, you're probably familiar with FFT shift. The reason we have FFT shift is to put the frequencies which are around 0, around DC, in the middle, instead of in the left of the plot. That's more convenient. So we have in the middle frequency 0, and all positive frequencies go to the right half of the spectrum, all the negative frequencies go to the left half of the spectrum. So that mode of displaying things is FFT shift, yes. And then the number of threads, which affects how many processing threads are used to compute the FFT in parallel using different CPUs and so on. And that you can leave as 1 unless you are really concerned with performance. So, all right, something we might notice is that these input and outputs are blue, but it's a darker blue color compared to all these ports. And the reason is that these are complex vectors rather than complex scalars. So these light blue are complex scalars, single numbers, and these are vectors. And the reason we have vectors is because the FFT transforms a vector of 16,000 samples in an output vector of 16,000 samples. So we need to give it vectors. There are a bunch of blocks to operate with vectors in GNU Radio, and oftentimes when working with vectors, we will be using stream to vector to obtain vectors, and also sometimes vector to stream to turn those vectors into a regular stream of scalars. So what does stream to vector do? It does something really simple. The parameter it has is the number of items. And what it does is it groups blocks of 60,000 adjacent samples into a vector of 60,000 samples. It's as simple as that. So that's the way to feed data into the FFT. Remember always to use this stream to vector block. Now we want to compute power. And the way to compute power with the FFT is to use complex to magnitude squared. You might know we have even mentioned that the power of a complex number is its magnitude or modulus to the power 2. When I said amplitude squared is power, I was referring to this squared. And many of the blocks you have in GNU Radio, for example, this complex to magnitude block can operate on vectors, but you need to set the vector length. The add block can also operate in vectors. So there are many blocks which can operate in vectors. And you need to set the vector length to match the vector size. Otherwise, if we put 3 here, for example, then we get mismatching connection because the vector size here doesn't match the vector size there, and probably there is here an indication that this size doesn't match that size. So, okay, NFFT. The next thing we want to do is to integrate, because we want to add many FFTs for a certain number of seconds, and I'm going to add a variable to define that. And the variable will be called integration seconds, and I'm going to set this to 5. That means that every 5 seconds, we will be adding all of the FFTs that have been produced within those 5 seconds and producing a single output, which is the average of, or rather the sum of all of those FFTs. That has the advantage that we are averaging out a lot the noise, so we increase our sensitivity. That has the disadvantage that we need to wait for 5 seconds to see something on the screen. So to do this summation, we use this integrate plot. What the integrate does is to add several consecutive samples or vectors. If we set it to NFFT, then it operates on vectors. And this decimation is how many vectors to add together. It operates component-wise. So the first component of all vectors gets added together. The second component gets added together, as is usual when operating in mathematics with vectors. It's just vector addition. And decimation is how many vectors we want to add together. So if I want to do integration seconds, I need to divide by how many seconds we have in each of the FFT outputs. And the way to calculate this is we have sample rate, samples per second. So initially we'll have 1 million samples per second, but we need NFFT of those samples to do an FFT. So the rate at which FFTs are calculated is sample rate divided by NFFT per second. So if I want to do integration seconds, I need to do integration seconds divided by this rate to know how many FFTs I need to add together to have 5 seconds worth of data. And for some reason, I'm getting 0 here. What's the reason? Yeah, it's not a division, it's a multiplication. So how many FFTs I have per second multiplied by how many seconds I want to have. So that's how many FFTs I need to add. And this works out to be 305. If you mouse over any of the fields, you might already have noticed that you get some information about its contents. So, okay, this is going to add up 305 consecutive FFTs and produce an output for us. I said we wanted the average rather than the sum. So the average is nothing more than the sum divided by the number of elements in the sum. And we can do that by using the multiply constant. And I would like to divide by 1 over FFT. And I think this is not going to work. Yeah, it is not going to work because since we have vectors, we need a constant vector rather than a single scalar. We need a constant vector but the way to do this is to repeat this 1 FFT, 1 divided over FFT, NFFT times, and we can do this with this Python signal. So this replicates the contents of a vector, and so we get a vector with, or a list, a Python list with 16,000 elements. Each of them is the same number, 1 divided by 16,000. So that's the constant we want. And then the next thing we need to do is to convert to dB units. because we are plotting things in dB units in this plot, and we want to emulate this plot. Oftentimes in radio astronomy, you will find plots which are not in dBs, because they do not need so much dynamic range. They are not representing both very strong and very weak signals at the same time. So dBs do not add so much value to those kind of plots. But for the kind of things we are doing today, where we have very strong signals together with very weak signals, having dBs is very useful. And okay, this is a log10 block, and it has an n in front. So the n is for n times log n. So if we set 10, this is 10 multiplied by the logarithm 10 of whatever is on the input. So setting a 10 here is the way to convert to dBs. And then NFFT is the vector size. As you can see, all of these blocks are being configured to operate on vectors. And finally, I need this repeat block for technical reasons. So what does the repeat block do? Repeat, as its name says, repeats its input n times on the output. So this, with this setting, 100 times on the output. What will this do for me? So every 5 seconds, I get an output here on the integrate. This is divided by 1/FFT. The logarithm is computed, and then I'm repeating the same output 100 times. The reason I'm going to do this is because I'm going to put here this vector sync, which is a way of representing graphically the contents of these vectors. But if I only feed one vector every 5 samples, the data might not reach here soon enough. So there are some buffers in between each pair of GNU Radio blocks, and those buffers oftentimes need to fill out. And if you have data flowing very, very slowly, such as in this case, one vector every 5 seconds, it might take a while, so much more than 5 seconds, for your buffers to fill up and send the information to the next block. And so the trick to have this repeat, and now we repeat this vector by 100. So every 5 seconds, we are actually generating 100 copies of the same vector and sending those to the plot. And that works better than just without the repeat. What do we need to set here? NFFT, and also the values for the axis. So because this is intended to represent any information you want, it's not restricted to frequency. So this might be whatever we want. And here it's going to be frequency in kilohertz. And what's the frequency start value in kilohertz? It's the sample rate divided by 1000, because I want kilohertz. And I also need to divide by 2, because the sample rate is my total bandwidth, but it goes from -500 kilohertz to +500 kilohertz. So this is the starting value for the axis. Now the step value, what it is, we have NFFT steps in the plot. Our data has NFFT points. And if it needs to cover sample rate divided by 1/3 kilohertz, in NFFT steps, the size of each step is going to be this divided by NFFT. So this 61 hertz we already computed before. And here I might write something such as power spectral density. If you see PSD somewhere, that means power spectral density in dBs. You can set your labels however you want. And I think this vector sync is ready to go. So let's test it. We need to wait for 5 seconds for something to show up. And now we get our plot, and we can draw a box here to zoom in. And we already see the advantage of using the custom FFT processing. So even though I have turned the averaging to the maximum value here, this is clearly much less noisy. So we are doing averages of 5 seconds. This is refreshing every 5 seconds. If you watch closely, maybe you will be able to see the noise floor changing. Just now it changed. But you can see how much nicer this is much more flat. And the advantage is that now we can detect weaker signals. For example, if we send our narrowband signal to another frequency, so wideband, sorry, I want to send the wideband signal to 100 kilohertz. As you can see, this only updates every 5 seconds. So every 5 seconds, we get an update rather than a smooth movement. It comes in steps of 5 seconds. But what I really want to do is to set the signal to noise ratio to something crazy low, such as minus 8 dBs. And in here, you can see this is exponentially dropping. This is averaging now. So, but you can see it. So you can also see it here, but maybe not so clearly. So here we are detecting a signal. I think we can even go to minus 13, or maybe that's too much of a stretch. We need to wait for a couple refreshes more. Maybe, just maybe, but something around minus 10 is clearly detectable with 5-second integrations, whereas in this one is quite difficult. So you can see it. It's the small hump in here. If I do something like so, maybe, yeah, here it is pretty evident. And the same happens with the narrowband signal. So the narrowband signal, we want to drop this to 20 dBs. And we can see, let's wait for another more refresh. Okay, this is completely clear. It can be seen here very, very well. Even maybe I think I can go as low as 10. And let us see how 10 looks like. No, it's gone. So how we might go about detecting such a weak signal that only has 10 dBs of CN0. That means it has the same power as the noise in 10 Hertz. I think here is a signal, but it comes and goes. So the trick is to make the FFT size larger, because everything, each quantity we have on each of these points corresponds to the noise measured in the FFT bin size. So if we make the FFT size smaller by making the FFT size larger, as we have demonstrated, the FFT noise floor will go down, our signal will stay the same, and we will be able to see it. So to do that, now I'm going to turn this up to 2 to the power 16. I'm going to disable this plot, or maybe I'm going to set it to the maximum value it can support. And then let's move this out of the way. Let's set this to 10 as I had before. And let's wait for this plot to update. And yeah, presumably here it is. So apparently, even so, with this FFT size, it's not possible to see the signal. But if we were to make this larger, maybe let's try 2 to the power 18. With a large enough FFT size, we would be able to see the signal. So let's try again. Frequency for the wideband, to move this out of the way, and let's wait for this. There it is. So now we can see our signal, and it's slightly above the noise because our FFT size is large enough that the noise power in one FFT bandwidth, or at least sometimes the signal appears. The way to improve this would be to also increase the integration time. So rather than doing 5-second integrations, we would do 10-second integrations, 100 seconds integrations, or whatever is required. Okay, let's resume. So before going further, I wonder if there are any questions, because I didn't stop for questions before the break. So if you have any questions about what we have seen, just ask them now or type in chat. Okay, good. So the next thing I want to do is to illustrate what we have seen about computing FFTs and spectral analysis of signals with two different cases of real world signals, if I have enough time to do that, and I think I will manage. Both are already on the repository, and the first one I want to show is spectral analysis W3OH. This uses a recording of W3OH done with one of the antennas of the Allen telescope array. W3OH is what is called as maser, OH maser. That means that there are some OH ions in space, and they are being energized by some physical processes, and then they release that energy as microwave radiation of a frequency that we can detect with our telescopes. And the frequency for this spectral line is actually 1665 megahertz, I believe. There is more information about this, by the way, in here. So here it says that frequency is this one, and the recording, if you want to download it, is in this Zenodo data set. So you can go in here, and there is more information about how it was recorded, when it was recorded, what is the format of the files, etc., etc. So this is something I recorded last year for these kind of tutorials. And as I was saying, this is a prototypical example of a spectral line. We have some astrophysical object which is emitting microwave radiation, and microwave radiation has a certain bandwidth because of different parts of the cloud of OH ions having different velocities with respect to us on Earth, or because of broadening of the spectral line because of other physical reasons. And studying these spectral lines gives us a wealth of information about the astronomical object. So it's important to be able to represent the power versus frequency of these spectral lines. Let me go back to what I had. Yeah, this. So what I have here is the following. I have downloaded the two recordings. I'm using the SIGMF data files. SIGMF is the signal metadata format. It's a standard way of sharing recordings together with their metadata, which indicates what's the recording format, when it was done, what's the bandwidth, what's the observing frequency, etc., etc. So it's commonly used recording format for raw IQ recordings. That means the raw complex voltages coming from the antenna. And here I have my SIGMF data file for polarization X. And here we have the SIGMF metadata file for polarization Y, because the Allen telescope array antenna feeds are dual polarization, linear polarization. So this would be X, which is horizontal, and this would be Y, which is vertical. And we will probably speak about polarization in another tutorial in more detail. So we have the two signals here. These are 16-bit integers, so we are converting them to complex and adjusting by a scale factor of 2 to the power 15, which is the maximum value we can have on a 16-bit integer to get numbers between -1 and +1, which is more common to work with complex numbers. And in here, I'm cheating a little bit because the gains of the two channels of the telescope were not the same. So I'm introducing here a factor 1.4 to make them have almost the same gain and basically to make the plot nicer. I also have a throttle block and I have multiplied this by 100. So this will process 100 times faster than real time. And the reason is that the signal is weak. So with a single antenna, the W3OH signal is rather weak, and we need an integration time of 100 seconds or thereabouts to be able to see something reasonable. And we don't want to wait for 100 seconds for the plot to update. So I'm simulating playback at 100 times faster than real time, and then the plot will update every second. And the rest is pretty much what we saw. The FFT size is only 4,096 points because, as we will see, we don't need very fine resolution. When we are trying to plot some spectral length which is broad, it is better to use an FFT size which is not so wide, because then we can integrate more FFTs. If we saw before, if I make the FFT size larger, then the number of integrations has number of FFT points on the denominator. So I get less integrations for the same integration time in seconds. So it's better to reduce the FFT size to have more averaging at the cost of less frequency resolution. And yeah, this is the same as before. Nothing has really changed. So let me play this, and after 1 second, we see the signal. This is the DC spike. It is an artifact of the receiver. Many receivers show some non-zero average value at DC, and it is best ignored, and it is best to tune our signals so that our signals of interest do not fall on the DC spike. So now that you know that this exists, you will see it on all the receivers. Sorry, this is the actual OH spectral line. We can see that all the signal is jumping up and down because of gain changes in the receiver. I'm not sure how long this recording is. Probably it's 5 minutes or so. So we are able to do 3 100-second integrations. And then the gain of all the receiver change is changing slightly over time. And this is what changes things to be moving up and down. And this also sets practical limits to the amount of integration that we are able to do. Without having some better gain calibration or some better gain stability on a real world receiver, we do not get so much gains from doing long averages, because if the gain is changing, you can imagine that the parts where the gain is largest get more weight on that average, and the parts where the gain is lowest almost disappear. So the effective averaging time is not as large. But anyhow, let me try to freeze it now and discuss what we see here. So certainly this is a rather noisy plot of the OH line. With the 20 antenna beamformer of the Allen telescope array, we would see a much nicer plot. But anyhow, still we can see here a double peak. And this double peak is a real signal. So this corresponds to this OH spectral line. having this particular shape. There are probably different parts of the same OH nebula that are moving at different velocities, and the different velocities cause different Doppler effects. This is essentially the velocity profile of the matter we are able to detect. So we see that there is some matter at this velocity, and there is some matter at this different velocity, and not so much matter at an intermediate velocity. So this is something that can be done, and in the beginning of August, we have the field day to the Allen Telescope Array. Probably we will do something which we have done other years, which is to observe the Milky Way, the hydrogen line of the Milky Way, in real time with the Allen Telescope Array dishes and GNU Radio. And we will see something similar to this in the sense that it's a spectral line, it's broadened over a certain frequency, and the shape tells us some information about Doppler. Okay, so this is one of these two demonstrations. Any questions about this OH spectral line? By the way, something we might want to try to improve the signal to noise ratio here is to average together both polarizations, both the X polarization, which is the blue one, and the red polarization, which is the red one, because this is mainly an unpolarized signal. So we will gain some SNR by plotting total brightness, and that's the sum of average of both polarizations. This is quite easy to do, so I leave it as an exercise if you want to try. Second demonstration, perhaps more interesting, another real-world signal. This is Voyager 1. Voyager 1 is the farthest human-made object currently, probably forever, unless we launch something which is much, much faster. This was launched in the 80s, I think, at the beginning of the 80s. And it's currently in interstellar space. It has exited the sun bubble and traveling in interstellar space. And we can even receive its signals to this day. In some years, it will be too weak to be received. And also the power supply it has on board, which is an atomic power supply. It has plutonium, I think, decays over time. So there's not so much plutonium left to power the spacecraft. But for now, we can still receive the spacecraft, do some science. And this is from not so many years ago. I'm not sure if 2000 or 2020, I want to say. I'm not so sure on the date. If you have your MJDs straight, your modified Julian days, maybe you already know what this MJD is. We're on 60,000 something now, so this was a few years ago. Anyhow, recording done with a green bank telescope. This is a 100-meter dish. It's the largest steerable radio telescope on Earth in West Virginia. So I have the recording here. It's an 8-bit recording on the README in the repository. There's the link to download the file. The conversion I do is very similar to the previous one, except instead of yellow for 16-bit, we have pink for 8 bits, and we have a factor of 128, which is 2 to the power 7, the maximum value we can have on an 8-bit signed integer. Then we take the complex conjugate, and the reason we need to do this is because of technical reasons about how the green bank telescope receiver works. The signal is flipped in frequency, so it's mirrored in frequency. And the way to mirror it back so that it is correct is to take the complex conjugate. You might know that taking the complex conjugate mirrors the signal. What I'm going to do is to disable all this part of the flow graph. I press D, or I right click and press disable. And now it's as if this wasn't anymore. And I'm going to re-enable the flow graph in parts as I demonstrate what happens. So what have I disabled? Yeah, these decimations I needed here. So, okay, the first thing I can show is the regular frequency sync. And there is not much to be seen. This at 0 Hertz is, have I turned average? Yeah, this at 0 Hertz is the FFT, sorry, the DC spike of the GBT receiver. Once again, there is an artifact because of the receiver. The Voyager 1 signal, I believe, is somewhere here, not to be seen with this kind of frequency sync. So we need to do our own FFT processing, and here we are using a large 65,000 point FFT to be able to see the signal well. So the rest is as before, stream to vector FFT, magnitude square, integrate, what integration length we are using, 1 second. And the repeat of 100 as before. And we are also doing dBs. By the way, I didn't mention, but here is one example in which we did not use dBs because all the signals were very weak. Those were physical signals having to do with radio frequency power being transmitted from natural sources. So not using dBs, using linear power units is more common than here, which is also a weak signal, but it's a telecommunication signal. So it's more common to use dBs to plot this one. So, okay, the settings of the vector sync are as before, and now we can see that a signal clearly appears here thanks to the much narrower FFT size. And we can zoom in, and what we see is a central narrowband signal. This is called the residual carrier, and it's used on ground to detect the presence of the signal and also to track its phase on the receiver. So this is there to help people on ground deal with the radio frequency signal. And we also see these symmetric humps on the spectrum, which sometimes change shape. This is the data which is transmitted by Voyager 1. It is telemetry data, so it is encoding some information about the spacecraft health, and maybe also about the science instruments, which measure usually some plasma-based physics about the outer space, electron density, solar wind, etc., etc. So this is digitally encoded and sent here. Most of the time when you see the signal of a deep space spacecraft, you will see this central spike, and you will also see two data subcarriers symmetric about the spike here. Maybe they are much closer together, maybe they are further apart, as in here. Maybe they are much wider, which means that more bandwidth is transmitted, so more bits per second are being transmitted, or maybe it's narrow, as in here. The trick of getting information across 70 astronomical units or so, I think, which is the distance of Voyager 1, is to transmit very slowly, and Voyager 1 transmits at 160 bits per second, and it takes about 1 day or so for the information to reach Earth from the spacecraft. So that's how you can see the data sidebands on the spectrum, and they do change shape because the data that is being transmitted is changing. There is actually some relationship between the shape on the spectrum and the contents of the data which is being transmitted. So far so good. What else we might want to do? Here we have basically 3 megahertz of spectrum, because this is one of the coarse polyphase filter bank channels of the Green Bank telescope. So you always get the recordings in these 3 megahertz blocks, but our signal only occupies these, I don't know, 50 kilohertz or something. So something we might want to do is to cut a piece of spectrum as I have done here, and to limit our signal processing to that piece of spectrum. And for that, there is a block in GNU Radio, which is called the frequency translating FIR filter. We will be looking at this in more detail on the next tutorials, but this is used to move signal in frequency so that it is on the center. We saw that the Voyager 1 signal was not on the center, so this block first moves it to the center, and then it applies a low-pass filter, which allows us to decimate the signal. You might know that when you decimate the signal, unless you do low-pass filtering, there is something called aliasing. So you always need to do low-pass filtering before decimation. So how we set this up, I have a variable called signal frequency, which is set to the frequency where the signal is located. Just basically reading from the FFT plot we had before, minus 379 kilohertz. I also have the decimation factor, 20. We are reducing our bandwidth by 20. So 3 megahertz divided by 20 is 150 kilohertz, more or less. And also we need the taps of an FIR filter. And the FIR filter is defined here with this low pass filter taps block. The ID I set here is a name which needs to match the name, which needs to match the name in taps here. And then these are basically the parameters we need for resampling without any aliasing. The cutoff of the filter needs to be below 0.5 times the sample rate divided by the decimation. Here I'm using 0.45 for simplicity, but I could also do 0.5 or whatever, as long as it's not above 0.5 times sample rate divided by decimation. And also the transition width of the filter, which determines how steep the skirts of the filter are. I will show this in a second. And also how much computation we need to do for the filter. So very steep skirts, which is the same as very narrow transition width, is great, but that requires a longer filter, and that requires much more computations for the CPU. So this is more or less appropriate. 5% or 10% of sample rate divided by decimation is usually what I use. And with this, we can do our frequency sync, and we can also do our FT processing. This is basically the same. So we have NFFT 60,000 points. This is actually NFFT2 in case we want to change this, but it's also 60,000 points. We also have, now we have 3-second integrations, so it's slightly different. And now since we have reduced the sample rate, this gives us more frequency resolution, because before the frequency resolution was 3 megahertz divided by 65,000. Now it's the output bandwidth we have here, which is about 150 kilohertz divided by 65,000. So the frequency resolution we get is about 2 hertz, and we can see here in comparison to 44 hertz. That's one reason to decimate, to get more frequency resolution with the same FFT size. And we are also using dB units. So let's see how the signal looks like. So let's see for a second, spectrum around signal, frequency sync. Maybe, just maybe, yeah. So with the regular spectrum syncing in a radio, we can see the signal. It's not great, but we can see here is the center, and here are the 2 data sidebands. So one way to make good use of the regular frequency sync of GNU Radio is to decimate, if we are able to do so, to just the bandwidth which occupies the signal. And by the way, I mentioned that I was going to say something about the filter skirts. So this is the transition bandwidth. The filter cannot drop immediately from passing signal to blocking signal. So it has some transition region. The width of this region in hertz is what we set by this transition width parameter. Here we have our spectrometer. So this is the 60,000 FFT with 3-second integration. And we see that maybe this FFT is a bit too large to display these data sidebands really well. But the thing I'm interested in is the carrier, which now is even easier to see than before. If we make the trick of measuring signal to noise ratio, we see that we have more signal to noise ratio here because the FFT beamwidth is smaller here than in the full spectrum. But the other reason why I'm putting up this plot is because you might be able to see what's happening to the signal. It's here now, and if I wait a little bit, this is being played back in real time, by the way. There is somewhere a throttle block which sets playback to real time. And as you can see, the signal is moving down in frequency. It moves a few hertz per second. The reason this happens is because of Doppler effect, or better said, Doppler drift. And so it happens that everything in space is moving, even the Earth. So mainly in this case, the Earth is spinning around itself. And by spinning around itself, that's what causes the position on the sky of astronomical objects to change through the day. So you have objects appearing on the horizon, then they rise, they reach culmination, and then they set down on the west usually. And what happens during this rotation of Earth, if you think about the geometry, is that when an object is rising, the observer, so the telescope on the Earth, is actually moving towards the astronomical source. And when the object is setting, the Earth is moving away from the astronomical source. And that movement, or actually not the movement, but the acceleration, which is the change in movement versus time, is what causes a Doppler drift. And so all the signals that we see from the sky will have superimposed on top of them this Doppler effect due to Earth rotation. They might also have a Doppler effect on their own, because if they are orbiting a planet, that orbit will also impart a certain Doppler effect. And there is also components of the Doppler effect due to the orbit around the sun. For example, Voyager 1 is in orbit around the sun. The Earth is also in orbit around the sun. However, that Doppler effect changes too slowly to be able to see it on an observation of a few hours. If we observe Voyager 1 at one moment in the year, and then we observe 6 months afterwards, we might notice that the Doppler effect has changed by several hundred kilohertz. And the reason is because of the Earth rotation around the sun. Maybe at some point, the Earth was moving towards Voyager 1. Maybe at some point, the Earth was moving away from Voyager 1. And I think that during some part of the year, the distance between Earth and Voyager 1 actually gets smaller because the Earth moves towards Voyager 1 faster than the distance with which Voyager 1 is escaping the solar system. But anyhow, this has come back to the right because the recording is played back in a loop. But anyhow, the reason I want to focus on this Doppler drift is because many human-made signals do not have this Doppler drift. They do not have Doppler drift at all because they come from stable electronics on Earth, not in space, or they have a completely different Doppler drift from the one which would correspond to Earth rotation, because maybe there are human-made signals on a satellite, and most satellites are either on low Earth orbits, which cause very high Doppler shifts, or on other orbits, but not in deep space, such as Voyager 1. So one way of trying to distinguish technosignatures from a human-made RFI is by looking at Doppler drift. And usually narrowband signal searches have some limitations in Doppler drift. They also check for a range of different Doppler drifts to be able to detect signals depending on their Doppler drift, but signals with no Doppler drift are usually ignored as being thought to be human-made RFI. So Voyager 1 is a great example or test subject for a technosignature, because it's a weak signal which is far away, which has the same kind of Doppler that an object in interstellar space would have. And that's the reason why Green Bank Telescope made this recording, and they do every now and then record Voyager 1 to check that all their instruments are working correctly for SETI detection. And this is basically all I had today. So any questions about this or comments about anything we saw?